Here is an example of a transistor amplifier that has been matched on both the input and the output lines. Here's an input, and the input line goes through a capacitor, which is used to block the DC values from reaching the transistor, goes through a capacitor, and then it meets the first matching stub, a distance D right here, and a distance L. Now the picture shown here is a microstrip line. On the bottom, underneath, is a copper line, and it's going to be grounded. This white stuff that you see is the sandwich or insulating material right here in between, and then on top, the line right there is the top part. So when we make a stub here, this is a parallel stub. It is always a parallel stub. If it's in microstrip, there's no way for us to make anything else, and this one is open-circuited. If it had been short-circuited, then we would have drilled a hole and soldered a piece of metal from the top of the stub down to the bottom of the ground plane. Then on the outside of the transistor is another transmission line and a capacitor that's been broken off in this picture. A distance D2 and a length L2 make another single stub matching network that is parallel, and it's also open-circuited. The two legs right here, this and this, are grounded. You can see that someone drilled a hole and soldered a piece of metal down to the outside. So this particular system has both input stub matching and output stub matching, both single parallel stubs with open circuits. There are a couple of reasons that you might choose an open circuit versus a short circuit. An open circuit is very tunable. If you make your stub too long, which you might do on purpose, you can then simply trim it down in order to tune it. If you have a short circuit, you're going to reduce the amount of electromagnetic compatibility problems that you have because there will be less transmission or less transmission out into the air than the open-circuited stub. So let's talk about how to add series lumped elements. What I mean here is, suppose that I have an inductor that I'm going to add in series on my transmission line. Here's my load, and there's my inductor right there. Actually, let me make a cursive L to represent an inductor. And let's say that that is a 1 nanohenry inductor working at 1 gigahertz. Characteristic impedance of the line is Z0. Let's say that my load, ZL, is 50 plus J50 ohms, and that I'm working on a 50 ohm transmission line. So if I want to plot this on the Smith chart, it's going to be 1 plus J1, a familiar point for us. And then let's say that it's connected onto a length of line that is 0.1 wavelengths long. We're going to do the same thing we've always done, which is draw a straight line from the center of the Smith chart through the point of interest. Since we're going to be rotating towards the generator, I'm going to use this outside circle that tells me wavelengths toward the generator, and I'm going to be reading this outside axis. Looks like I'm at about 0.162 wavelengths, and I need to go 0.1 wavelengths, so I'm going to go to 0.62 wavelengths. Let's just look along the outside here. Here's 0.235, 0.26, there's 0.262. So again, I'm going to draw my straight line down through the 0.262 point, like this, and then I'm going to use my piece of paper to mark the magnitude right here so that this distance is the same as that distance. And this value right there I'm going to call ZA. Here's the A point right before I get to my inductor. Now if I'm going to add an inductor, its impedance is going to be in ohms. So the impedance of the inductor is going to be J omega L, which is J times 2 pi. My frequency is a gigahertz, and my inductor is a nanohenry. So right here I need to read ZA, and I need to get it in ohms, and then I can add it to ZL. So ZA is going to have a real part right there, an imaginary part right here. The real part is about 2.5. The imaginary part is negative 0.55. And I'm going to move on to the next lecture because I'm almost out of time here.